Test. Okay. Oh, Haley. Oh.
Hi.
Oh, nice seeing you connected. Let me make you co-hosts so that you can watch incoming visitors, if any. Okay. So, yeah, would you please watch any? Oh, okay. I see Hadassah myself, but if I miss, please watch them. Okay. Hello, Hadassah. Nice seeing you connected. Let me quickly make you co-host as well. My co-host, yes. Hello, Hanman. Nice seeing you connected. Okay, so we are trying to go really quick, and today will be another speed up. So prepare. I will try to squeeze information. It may need to watch it later for additional details. So we here is the homework. I just looked back on it and tried to expand. So those who complete by tomorrow evening will get extra credit, substantial extra credit. Who cannot do it by then, just do it by coming Monday for regular credit. And most important thing is a question B, to compute absorption spectra for all oligomers. Part C is something that we will try to do by the end of today's lecture. Is if time allows, it will be flow chart of the density functional theory. But even if you do it in class, please do it at home and then send as a part of your homework. So many thanks to those who have voted on the presentations. I'm really happy to see your enthusiasm, and I think the majority already voted, and I'm very happy to see that there were volunteers for molecular dynamics, which is second most important. The first most important is light to matter interaction that Hadassah has selected, and second most important is the one which is yet open, from heating to molecular dynamics. Okay, those were keys to homeworks from previous years when we were doing spin polarized density of states with WASP. I just do not remove because it's nice images, but we will do something different tomorrow. Umar, nice seeing you connected. And here are just optional suggestions to those of you who do not know what to select for the project. Okay, when we met yesterday, we reviewed first Hornberg-Kohn DFT theorem and proved the second one. So if we do know the density, it unambiguously defines the external potential. Theorem number one. Theorem number two, if we know the density of the ground state, then it gives unambiguously the minimal total energy, the energy of this ground state. Which means if you take any other density, it will give bigger energy, larger energy than the energy extracted from the rho node, rho sub zero. But these theorems do not tell how the energy is extracted. Then we did a little. Hello, Mara. Nice seeing you connected. Thank you for voting for one of the molecular dynamics subjects. It's quite important, and I'm happy that there are volunteers for this. So on the last 5 minutes of yesterday lecture, we went through these little lines, which is a derivation of introduction of the functional derivative. So we need to learn the following following logical diagram. So and it will be a goal for today. So from density we need to get potential, from potential we need to get orbitals, and then we need to close a loop, and from orbitals to get density, and in the middle we can get total energy. And the little derivation we covered yesterday was that if we know, we can extract contribution to electron to nuclear interaction based on knowledge of the external potential and density. We just need to integrate them. And if we submerge derivative of the space, derivative of the volume, if we combine it with the density distribution, we are getting an increment of the density. And now we can remove the symbol of integration and just develop. So if you remove symbol of integration, then we will get a little increment of the energy. And then we just, as in the next line, and then we just formulate the fraction. So increment of energy, electronuclear energy, in respect to increment of density, gives us the external potential. And in the limit of increment of density goes to 0. So it is a definition of functional derivatives, derivative, which is an extension of regular derivative or partial derivative. So if you know energy or portion of energy, if you know the density, we can construct derivative and extract the potential. So basically it is the step here from density to potential. It is very, very important. Okay, next goal that I want to cover within maybe 15-20 minutes. Well, how to go from potential to orbitals, it's quite natural. But then the transition from orbitals to density will need a little derivation, just giving you a heads up. Amir, I'm happy to see you. Thank you for connecting. Okay. So there will be several fragmentary little pieces of information, and not all of them are critically important. The one I'm telling right now is I wouldn't say unimportant, but it is a secondary thing. So you can relax for a few minutes. So when we were studying the Hartree-Fock theory, one of the fundamental knowledge that we extracted from this exercise, that electron-electron interaction does have two portions of energy, Coulomb and exchange. And exchange energy has negative term. It is stabilizing portion of electron-electron interaction, and it originates from antisymmetry. In addition to Coulomb and exchange, there is a third part of electron-electron interaction. It is called correlation. And basically, this is represented by a little diagram here in the red box. So suppose you decided to come into the class. Suppose we set up a little game. I took a chair in the middle of a class, invited 2 volunteers, and asked them to run around the chair. And when anyone in class is clapping, both of them should try to sit on a chair, right? So it's evident that only one can sit on a chair because the motion of these two objects around a chair is correlated. From time to time, one person is blocking a seat, right? There is a same when one looks onto electron-electron interaction, like multiple electrons, there is a contribution to the energy of the same nature, like total energy of the density of interacting electrons will be different from the total density of electrons which with partial product of one electron densities. So the box in yellow, rho x, rho y approximately equals rho x times rho y is approximate. There is a, because it is not exact. When electrons more than one, they feel each other and they change their shapes. So here is just a very little illustration. It's not on a level of mathematical proof. So suppose we just put two electrons in one-dimensional box, assuming that we all are comfortable with the concept of particle in a box. Excuse me. Then if these electrons are independent, we can tell that for one, I think it should be not cosine but sine if you start at 0. So for one electron it will be sine for probability or charge distribution, and for another it will be also the same harmonic. And if you do two-dimensional product, it will be distribution with maximum in the center, and it will be symmetric, repeating the form, like looking like a square. But if we allow electrons to experience all forms of interaction, this shape will change. There will be deviation from this symmetric form, and the position of first electron and second will be not independent from each other anymore. So the way to take it into account on a regular way with wave function needs so-called perturbative theories like MP2, configuration interaction, CI, or coupled clusters. But density functional theory accounts for this effect by including this interaction into the functional. Okay, it was just a little comment about the 3 types of electron-electron interaction. Now, I am starting another little fragment. It is important intellectually, but not so important for practical things, for practical computation. It is about of the same importance as theorems that we covered on previous 2 lectures. There will be, for this little fragment, there will be no more equations that I will talk only about 1 slide, but the amount of words is a little larger. So in our regular world, electrons do interact to each other, right? They repel, they experience this anti-symmetry based exchange, and they have correlation. The total energy is constructed of kinetic attraction between electrons and nuclei and electron-electron repulsion. So if you are interested in this subject now, please try to follow what I'm saying. I'm not the best in explaining it, but the concept is in words, not in the equations. So the theorems operate with total energy and total density. The theorems do not prove how the energy is partitioned between different portions of energy. It doesn't tell that kinetic should be bigger than electron repulsion or smaller than electron to nuclear attraction. So the partition of energy between these contributions is to some extent our freedom if we are theory designers. Theorems do not give restrictions. If we want to literally mimic what happens in nature, yes, we need to follow exact contribution from electron and nuclear to electron. But if you just formally want to follow the theorems, we can change relative contributions of different types of energy and get the same total energy and fulfill all theorems. Let's make a little vote and just approve this statement. If you just agree with the idea. Okay, yeah, thank you, Hadassah, thank you, Amara, thank you, Hanmant, thank you, Amir, thank you, Haley. Lola and Umar, if you disagree, just ask a question or express your concern. Concern one. Huh?
Can you explain this concept again?
Are you okay or not okay?
I said, can you explain the concept again?
Oh, okay, yes. The energy, total energy that, let me, yeah, total energy and total density are players of the theorems. So theorems teach us that energies and densities are, energy and density are related, and there are some non-ambiguous conclusions. But the theorems do not tell which of the contributions to total energy should be bigger or should be smaller. So if we take a little piece from electron-nuclear interaction and reassign it to electron-electron, or otherwise take a little portion of energy from electron-electron repulsion and reassign it to electron-nuclear attraction, theorems will be not violated. We only need to admit that monitor that the total energy for given density is fixed, is a constant. Oh, is it better now?
Yes.
Okay, Umar, would you admit this statement? Your raising hand means you accept or you have a question?
It's perfect. Thank you. It's good.
Okay, yeah, thank you. Okay, now another little contribution to the Nobel Prize of Walter Kohn. Now, let's assume that there is not one universe in which we live, but infinite amount of universes, and they are continuously labeled by index lambda. And this lambda takes value from 0 to 1. So if the lambda equals 0, it is real world where we live. And if lambda is bigger than 0, larger than 0, then it is something different, parallel world, auxiliary world. Now, in each of these worlds, our theorems for DFT will work, because the proofs didn't tell about partition, but let's design this electron nuclear part of energy and electron part of energy in the following way. The electron portion of energy will have a prefactor 1 minus lambda. So if lambda is 0, then it will be at full extent. If lambda goes to 1, this electron interaction will disappear. But in order to match the total energy, we will increase or decrease the electron nuclear interaction energy, and we will label the updated electron nuclear energy with the index lambda. So once again, if lambda is 0, it will be electron nuclear interaction in our real world. And if it is bigger than 0, up to 1, it will be a parallel world. So I hope everyone is happy with this science fiction of the parallel world. And why do we need it? Not only to entertain ourselves with some fiction. There is a practical goal. The electron interaction is very hard to deal with if you really want to construct determinants, find all terms. We want to simplify the numerical procedure. And if we can assign the energy of electron interaction to electron to nuclear attraction, just by the nature of these objects, the calculation will be much simpler. So we do not violate theorems. We keep the same density and energy, but we reassign portion of energy from electron repulsion to electron nuclear attraction. And I believe the formal part of this trick is related to differential equation chapter on Lagrange multipliers, but I'm not sure. Okay. So in the auxiliary universe, electrons do not interact to each other. So in the auxiliary universe, 1 minus lambda here, 1 minus lambda. In the auxiliary universe, the electron term is removed. And then the total energy is expressed as kinetic energy plus contribution from electron nuclear attraction. So I think the right word is we repartition the contributions to total energy. So just bigger weight to one electron term. Okay. Now, why we do not use orbit? So done with auxiliary world. Now we are going to start another little section on the way how to get orbitals out of the potential. So why do we need orbitals? Because in terms of orbitals, it is very easy to compute kinetic energy. And just in case, here is a little summary of the first lecture in quantum mechanics. So kinetic energy in quantum theory is the same, it has analogy to classical theory, where it is mass times velocity squared over 2 or momentum squared over 2 masses, right? But if you want to do quantum, we need to replace momentum by a derivative over position. And if it is momentum squared, then it is a second derivative over position. And this formulation in terms of this quantum operator is a very numerically efficient way to assess contribution from kinetic energy better than direct assessment from function. So it is the only reason why we are going to use orbitals in next slides, and why it is used in like VASP, Gaussian, and other pieces of software that where DFT is implemented. Okay, so total energy minus kinetic energy, symbolized by letter T, in the auxiliary world will give only electron to nuclear attraction, right? Because we did remove, I think it should be one here, because we did remove the electron-electron interaction by repartition trick. So by subtracting total minus kinetic and taking functional derivative of this contribution of energy over the density, one is getting potential. So now we are going to use this potential in order to generate orbitals. So in the auxiliary world, the wave function can be obtained as a solution of Schrödinger equation, which contains kinetic energy, potential energy, and then it allows to get multi-electron wave function and get the energy. And the potential, probably one should write a summation and make individual potential for each degree of freedom. I just do not want to change. Okay. Summation over I, V of Ri, but it is the same potential for each electron, which means that we can chop this big Hamiltonian onto several small Hamiltonians. The chopping of multi-electron operator on a single electron operators is a dream of a mathematician. So it is a literal practice of the separation of variables trick. So if you want wave function of many variables to be product of single variable functions, then differential operator should be summation of the single variable operators. And here, literally due to all of our tricks, and most specifically due to the trick of this auxiliary world, we exclude electron-electron interaction, and it enables us to practice separation of variables. So because we remove electron-electron interaction in the auxiliary world, the Hamiltonian can be chopped on a summation of independent small Hamiltonians, and it is symbolized by lowercase h. So H1, H2, H3, which are specific Hamiltonian for each electron. So we practice separation of variables. Please vote if this concept looks reasonable for you, unreasonable, or you need more comments. Okay, thank you, Hadassah. Hanmand, Amara, Haley, Amir. Do you need more comments, or it is a thank you, Lola. Umar, do you have requests for comments? Request 1, request 2, request 3. No requests. Okay. So since the H1, H2, H3 are the same, they are composed of the second derivative over space, which is kinetic energy and potential. So the little Hamiltonians for little one electron wave functions will be absolutely the same. We will have as many identical equations as many electrons we have. So therefore, we need only one of them. Okay, so Schrödinger equation for one electron with, instead of full Hamiltonian, it will be lowercase Hamiltonian. So this equation is derived by Walter Kohn and his team member Sham, and it is named as Kohn-Sham equation, and the orbitals that are coming out of it are named Kohn-Sham orbitals. So it is a major breakthrough in making DFT practical and doable. So, and we have, it is a one electron Schrödinger equation, which will get a lot of orbitals. In some sense, they are related to molecular orbitals in Gaussian, but correct terminology is to say that those are Kohn-Sham orbitals because they are made for the auxiliary world where electrons do not interact to each other. Okay. So we are done with getting orbitals out of the potential, right? So we went from multi-electron to single electron. Lowercase Hamiltonian is Kohn-Sham Hamiltonian, and then the multi-electron wave function will be of the ground state will be composed as a Slater determinant of all occupied orbitals, as many orbitals as many electrons. So it's not a simple product, it is a Slater determinant. So it will be multi-electron wave function in the auxiliary world where electrons do not interact with each other, but the total energy of this system in this world will be the same as the total energy for the same molecule in our world. Okay, this section is done. I'm switching gears and going to the next section. Now, so here is the little, we went from density to potential. We went from potential to orbitals. And now we need to close the loop and go from orbitals back to density. So the question is how to extract total density if we do no orbitals. There is a derivation that I want to demonstrate. But the answer is very simple and expected. So density is, I think we use this definition at the very first lecture on density functional theory. So we just take each orbital absolute value squared and add together all these orbitals for all occupied orbitals, and it will be density. But now it is time to give a little proof to this statement. Okay, so the density of many electrons, multi-dimensional density, will be multi-electron wave function of all independent positions, absolute value squared. But this density will depend on like as many positions as many electrons. It is not what we need, because if we would have this multidimensional function, we will automatically neglect all benefits of DFT. We want a simple theory that is easy to compute. So we are interested in projection of multi-electron, multi-variable density onto a single variable. So how do we do such projection? What is the definition? So if we want the density to depend only on, here I'm focusing on this green box, only on argument on position of the first electron. And I do have density depending on all electrons from first to electron number n. I should take this second green box density of all electrons and subsequently perform integral over position of second electron, integral of position of third electron, integral of position of the last electron. So if this function of n variables is integrated n minus 1 times, the resulting function will be depending on one variable. Make sense? Okay, yeah, thank you. Now I'm going to practice this recipe, this prescription for the case of 2 electrons. So I will formulate Slater determinant for molecule that has that has only 2 occupied orbitals. I think the only example is H2 molecule, right? But here I'm not specifying. So orbital number 1 in point 1, orbital number 2 in point 2, Slater determinant. And I'm going to integrate this Slater determinant over position of second electron in order to get density as function of position of 1 electron. So I am targeting to get density that depends on a single Cartesian, like 3 Cartesian projections. Make sense? And this is an object that is very comfortable to treat numerically. And this is the object that I want later to plug into this feedback loop to compute potential, compute energy and potential, and then close the loop. So I am going to focus on the lower green box and write it literally in all details. And I invite you just to follow it. If you're really curious, you can try to reproduce it, but maybe following will be sufficient. Okay, it's not the hardest part in our course, but it needs a little coffee alert and attention. So Slater determinant for 2 by 2 matrix is the product of diagonal elements minus product of subdiagonal elements, right? So it is this green fragment minus purple fragment. If I am going to construct the multi-electron density, I need to multiply wave function by wave function conjugated, where I just assign this star complex conjugation to each orbital. So after I do have this psi and psi star, depend multi-electron things, I'm going to multiply them. And since I need to get 1 electron density, I will integrate it over position of the second electron. So what I'm doing is rho of as a function of first and second positions of electron integrated over all positions of the second electron, and it should give me 1 electron density. My goal, which I will prove in like 2-3 minutes, will be to get the following equation. So rho of R1 must be equal to theta 1 of R1 absolute value squared plus theta 2 evaluated at point R1 absolute value squared. So which is summation of all occupied orbitals at point R1 absolute value square. I goes from 1 to n. So by now we do not have a proof, but I intend to prove this expression. It is not, well, the answer looks simple and reasonable, but it is not immediately self-evident, because you see, we have if you do things literally, we have quite bulky object. We have like 1, 2, 3, 4, 8 single orbitals. They are constructed in terms and products, and who knows what will come out as a result. Okay, so here I'm opening this expression. So I'm just the greenish part comes from diagonal portion of the Slater determinant, and purple comes from off diagonal. And then we have wave function with conjugation times wave function without conjugation. So there are two terms in first bracket, 2 terms in second bracket. So if I open the brackets, there will be 2 by 2, 4 terms, right? Okay, let's do it carefully. So 4 terms, and these terms will include 4 orbitals in each. And these 4 orbitals will have the portion that depends only on R1, and it will have portion that depends only on R2. So the portion that depends on R1 can be put outside of the integral, and the portion that depends on R2 has to be integrated, right? So by processing this expression line by line, we are going to focus on the dependence on R2 and use the orthogonality relation. So orthogonality relation is that if we did everything correctly, then orbital I of R2 times orbital J of R2, integral dr2, will be either 1 or 0. So it will be 1 if indices I and J are the same, and 0 if indices I and J are different. So this property of orthogonality naturally comes from any healthy solution of eigenvalue problem. If the solutions are non-orthogonal, it is a big problem. So it is a typical property of solutions of the eigenvalue problem, especially Schrödinger equation. Before we go forward, let me just double check if everyone is happy with orthogonality relation, that it doesn't look insane to any. I support orthogonality. Amir supports orthogonality. Haley supports orthogonality. Amara supports orthogonality. Hanmant is not sure. Umar supports orthogonality. Oh, Hanmant is.
Dr. Kilin, but I have one question.
Yes, please.
So why do we consider the complex conjugate term here, θ1 star or θ2 star here?
Okay. Anyone wants to help and answer instead of me? Hadassah, would you like to try and just tell why we need to multiply wave function by its conjugated if we need probability distribution?
I guess one reason why is if you do that, any imaginary parts will be taken care of, since the complex conjugate makes any imaginary numbers negative. So that's, I guess, a mathematical motivation. Otherwise, that's just the definition, I guess.
Okay, yeah, thank you, Hadassah. Hanmant, is it okay, or you want a little bit more?
It will be better if you elaborate a little bit.
Okay, so the theory of quantum mechanics that introduces concept of wave function is defined so that the definition of wave function is the object which, upon making this operation, gives probability distribution. So it is just definition of how quantum mechanics works. So we are not designing it intentionally for computational chemistry or density functional theory. It is just one of the postulates, one of the axiomatics of quantum theory. So it is just, first, it is definition, as Hadassah told. The second motivation is that wave function can have imaginary parts, which I'm not comfortable. Like if it has, like if there is a complex number that has like x plus I, y, right? If we make a construction where we make a conjugation of the first part, conjugation changes the sign in front of imaginary unit. So it will be x minus I y, x plus I y. And then one practices the, if this is A, this is B, A squared plus B squared plus just opening the brackets. I can live without this equation. Just it will be x squared. Then for the second part, it will be minus y squared, and then it will be minus I y x plus I y x. So the portions with complex contributions will be cancelled. So this complex conjugation, as Hadassah completely answered, removes the imaginary part. Okay, yeah, thank you. So for processing this 4 lines further, we are going to use the orthogonality relation. Orthogonality. And we are going to look if here index 2 equals index 2. So 2 equals 2 means the orthogonality will give 1. Now we look on dependence on R2. Here is index equals 1. Here index equals 2. So 1 is not equal 2, so it will give 0. Again, looking on dependence on 2, here will be index 2. Here is index 1. 2 is not equal 1. Orthogonality will give 0. Last term, dependence on R2, index 1 is index equals to index 1. 1 equals 1, it will give 1. So by now, each term originally was containing product of 4 functions. But through orthogonality, we integrate out and remove 2. Right? In addition, we have just proved that the 2 middle lines will be cancelled because something is multiplied by 0 is cancelled, right? So we will have only the first and last. And in the first, we will not have integration anymore. We will not have dependence on R2 anymore. So we will have only product of theta 1 in point 1 star, theta 1 in point 1 without star. Same story in the last line. So we will not have integration, we will not have dependence on R2, and we will have theta 2 evaluated at R1, theta 2 evaluated at R1. Right? So here we have first orbital, and there we have second orbital. So we arrive to the expression that I declared as an expected answer. Let me see, there should be, yeah, it's very ugly, but I was trying to do it from year to year. So from the first line, we are getting theta 1 squared. From the last line, we have theta 2 squared. And as a result, we are getting this equation that summation theta I absolute value squared. So we have obtained the equation, the protocol, how to get density out of orbitals. And now we have all components. From density, we can get potential. From potential, we can get orbitals. From orbitals, we can get density, and then loop it together. So one of the questions for your homework, last question, is to write down most important equations in the form of Microsoft Word equation editor, because we will need it for reports on the project in the future. So here are the main equations. So total energy is extracted from density, and it is symbolized by these rectangular brackets. Right now it's too early to say explicit form of functional, and most authors do not tell it. They just put rectangular brackets. Then one can get potential as subtraction of total minus kinetic and applying functional derivative. Then as soon as we have potential, we can write Kohn-Sham equation for Kohn-Sham orbitals. Some people add indices Ks here. And then the Kohn-Sham orbitals allow to construct total density, and everything is done in the auxiliary world where electrons do not interact to each other. But this first equation for total energy is constructed in such a way so that it includes contributions from electron interaction. So here are the equations, and here is our goal to do the same thing as we have done twice in the past. So at the end of each chapter, we were converting equations into a flowchart. So first, we converted optimization of interatomic energies into flowchart, right? At the end of the second chapter, we created a flowchart for finding expansion coefficients in atomic basis for Hartree-Fock procedure for finding total energy. Now we need to make a flowchart for density functional theory, which is not a big deal. We already have it, like density, potential, orbitals, and then we need to make a loop out of them. So your home, I hope we will finish it right now, but with or without help in class, I encourage everyone to fill this form at home and append it to your homework to make sure that that you have feeling of how things are working. So right now, I'm going to copy this little link, send it to everyone in the chat line. Paste. And invite everyone to go on this link. Request access. It will not work. Yeah, it would delay things. Oh, yeah. Then yeah, it is my fault that I didn't arrange. It will take too long to make access, and our time is too precious. Let's do it just in the regular way. It's already the answer. Okay, please try to do it at home, but the idea is that yeah, I messed up the pedagogical steps. It is typically a big fun doing it together in the class. So the equations are put aside, and then everyone in the class is moving equations and placing them in the box. But you can imagine that we are playing this game right now. So Here is how density functional theory is working. We have input and output. So at the input, we do have positions of nuclei, number of electrons, and tolerance limit, which tells when to stop the protocol. On the output, we have total energy as function of atomic positions, right? So everything inside is just a black box that has to work. So when we start density functional calculation, we make a guess density, like educated guess based on other theories, or WASP software doesn't bother to make educated guess. They just populate the space with random numbers, because the algorithm is so perfect that it will, through self-consistent procedure, it will make correct answer out of any garbage. And WASP literally starts with random numbers distributed in space. Then one is getting a, again, first guess of the potential based on this density. So probably at the first step, there is no kinetic energy, and one is just using equation for total energy, practices derivative, and then plugs it into Kohn-Sham equation. The Kohn-Sham equation computes orbitals. Orbitals are plugged into density, and this density is forwarded again to the cycle. At each, and then it is repeated again and again. At each step, the total energy is computed, and subtraction of old and new energy is compared to tolerance limit. As soon as their subtraction is getting smaller than predefined value that by default was give some number, but we as humans can make it smaller or bigger to make calculation either more precise or quicker. One is getting answer. So total energy is something that is expected to be correct based on the theorems. Orbitals that we are plotting, they are not ideal. They are not our orbitals from our world. They are orbitals from auxiliary world where electrons do not interact with each other. So we should be careful in explaining results based on the orbitals derived from WASP. But with all these ideas that orbitals are from different worlds, they still give very good qualitative analysis of properties and molecules, and it is okay to use them if we make a disclaimer that we recognize that it is not an exact orbitals from our world. And some researchers, as Professor Krzyzewski, who is advisor of Hadassah, are using the Kohn-Sham orbitals as a basis for more advanced and precise calculations. So Kohn-Sham orbitals are a good thing. One just needs to know their limitations. Okay, now I'm going to do a really crazy thing that I hope you will enjoy. So at the end of the first chapter, we had this diagram, which was the flow chart of geometry optimization, right? Do you recognize it? More or less? Okay. We had the increment of position as a function of potential derivative times the square of time increment. And then we were comparing the change of total energy as a response to change of the position until we arrive to the minimum, right? In this procedure, there was one black box where we were computing potential or total energy as function of position of ions, right? Now it is the day of glory. Now we have much better picture. In this black box, one can plug in the Kohn-Sham procedure, because Kohn-Sham procedure on the previous slide is exactly what converts positions of ions into total energy. So for each position of ions, we get new total energy. So let's shrink the diagram from previous slide into this black box and plot them together. Black box. I'm just expand this box a little bigger, right? And put the CHEM676 diagram here. Now we do have a plan how to reprogram the WASP software. So how to reprogram any software that does geometry optimization. So we have two loops inside of each other. Outside loop modifies positions of ions. Inside loop modifies electronic structure. So at each iteration of ionic position, of search of ionic position, we come to the stage where we need total energy as function of these ions, and we repeat this electronic cycle until self-consistency is arranged. Then this energy is forwarded to the subroutine, to the unit that computes the gradient and follows on the potential energy surface, and then we keep going. So when we look into the WASP file that is named OSZCAR, it gives us report of how we are progressing over these cycles, over both electronic and ionic cycles. And when we meet in the lab, I'm going to cover this aspect. Or here is an example how the OSZCAR file looks like. So there is an outside ionic steps, and in each ionic step there are several electronic steps. Sometimes there are just a couple, sometimes there are up to 60. But and here there is a energy offset between total energy. So it comes to convergence. It's small. As soon this column gets smaller than tolerance limit, we are finishing the cycle. So it's old total energy, new total energy, and their subtraction. As soon it converges, one gets to new ionic step. I think we achieved a lot. So we've got the way how to extract potential out of density. We got orbitals out of potential. We got density out of orbitals. We got algorithm, and I really want us to cover practical steps of WASP during Wednesday lab and present them on Monday and Tuesday. I will try my best to make it possible. If something will not work, we'll postpone, but it is very undesired outcome. So I'll try to intensify tomorrow's lab as much as possible. Okay, so meeting is done. Everyone is welcome to disconnect, and I will stay here to answer any questions.
Thank you.
Thank you.
So Dr. Killen, I have a question. So in the homework, when you said to plot the orbitals, do you mean using the CubeGen to plot them?
I don't care.
Oh, okay.
Let me explain why I do not care. We are going to do research.
Right.
The VMD or CubeGen and Gauss-U are instruments for our research. And as researchers, we all should care about the final results.
Great.
Right. So I would do it with VMD, but if by some reason you prefer CubeGen and Gauss-U, go ahead. Like if you need to arrive to a conference and give presentation at a certain date, it doesn't matter whether you fly or drive or walk. It only matters that you will be there at a given time, right?
That's correct. Thank you.
Okay. Yeah. Thank you for the question.
Yeah, I have a question.
Yes, please.
So,
Well, and
Um,
I'm not hearing well. If you enable camera, maybe I will recognize better if you're comfortable.
okay. So I remember that when we really like watched the Aussie car, I don't remember us specifying the tag NELM. So does VAST have like a default for that tag? Because I only remember that we just do NSW equals
60, 60.
oh, so it assumes 60. Is that what you're saying?
Yes, if the electronic iterations do not converge before 60, it will be broken at step number 60 by default. If you really know what you are doing, you can just manually add this keyword into in-card. Like if you need higher precision, you can put NELM equals 120. If you do not care about precision, for some people like Aaron was working with a system that has 3,000 electrons, and it was converging very poorly. It was just stopping calculations. And then he made NELM equals 6 just to complete the cycle and get something, and get some very imprecise wave car. But then after one step was completed, he was repeating again and again. So you have a freedom to play with these parameters.
Okay, I've also seen a tag that says NLM min and NLM max, I think. Does anything like that exist?
I am not ready to answer this from the top of the head, but I think designers of VASP recommend an elm to stay within ranges. So if one makes an elm smaller than 5 or smaller, the results will be completely unreasonable. So it's not recommended, or maybe it's even forbidden to do. So it should be the minimum is 5.
Yeah,
And
I saw what the one I saw was minimum of 5 and then maximum of, I don't remember. I mean, it was 60 or something. I really don't remember now.
okay, it is some experts in VASP from whom I was learning like 15, 16 years ago. They were just sharing experience that if system doesn't converge in like 60 or 100 NELM steps, then it is just bad system. Just throw it away and study something different.
Okay. Okay.
That's all?
Yeah, that's all.
Okay, yeah, thank you. Thank you for the questions.
All right. Thank you. Bye.